Swayam Prabha. Digital India. Educated India.
So, last class I have discussed about the beams resting on elastic medium, and then I have discussed that the beam can be resting on a spring or it can be resting on a 2 parameter model. So, now today I will discuss about the beam resting on spring. So, before I go to that part, now as I mentioned that this foundation can be idealized either by beam or by plates, and as the title of this topic is beams on elastic foundation or elastic medium. So, but I will not discuss about the plate thing, but you should know that the foundation not only can be idealized by beam, it can be idealized by plate also. Now, in that case the plate can be also infinite plate, that means pavement subjected to aircraft or traffic loads, and that means infinite wrap foundation subject to highly localized load. That means if in a wrap foundation where a particular area the loads are concentrated on that particular zone, then that can be idealized by infinite plate. Then pavement can be idealized by infinite plate. Then the plate with finite length can be rectangular plate which finite L and B. Then circular plate, that can be the circular wrap foundation, tank foundation, and similarly it can be on the 2 parameter model and the nonlinear spring, time dependent effect, all this can be incorporated. That means the circular wrapped, circular tank, those can be idealized by plate also, and I have already discussed that which are the conditions will idealize by beams. So, these are the conditions which you can idealize by the plates. But I will discuss the first that beam resting on spring. Okay. So, this is the topic, that beam resting on plate, beam resting on spring. Okay. So, that means this is a beam which is resting on plates. And whose subgrade modulus is K, and the beam is subjected to UDL Q. Okay. Now, so here this beam has a finite width. So, that means if I draw the cross section, so this will be the cross section which has a finite width B and a thickness of the beam is H. H is the thickness of the beam and B is the width of the beam. And then we have to go for some sign convention also. Now, if I take one small element, say one small segment over the beam. So, this is a small segment, say, that I am taking. This is the small segment that I am taking. So, if I draw this small segment, suppose this is the small segment, okay, I am taking, and that segment thickness is dx, because this is in x direction. So, that thickness is dx. Okay. So, that means this thickness is basically dx. So, this is dx, UDL Q is acting over there. So, total load acting on the top surface of the beam due to this UDL will be Q into dx. Okay, so that is Q into dx. So, that is the UDL which is acting. So, let me draw in better way. So, this is the UDL acting, that is Q into dx. Okay, or I should write this is Q into dx. Okay, and there will be a reaction will act at the bottom of the beam, and reaction will give you the reaction, these springs will give me the reaction. So, there will be a reaction that will be bottom of the beam, and say that reaction will be P into dx. The reaction is P, total reaction force is P into dx, and in this segment there will be a moment. This is the left side, there will be a shear force Q on the left side, and right side there will be a shear force Q plus dq, and there will be a moment M plus dm. So, these are the forces or the free body diagram of the small segment. That means, the left side moment and the shear force, and this is the shear force plus dq and the M plus dm, and these are the two, one is reaction force, another is the external force is acting on the small segment. Now, the sign convention that you have to consider, I am writing that the upward acting shear force Q to the left side, to the left of the cross section or left of the segment is positive, and the corresponding clockwise moment acting from the left side is also positive. So, what does it mean? That the left side upward acting shear force is positive, and corresponding bending moment, which is clockwise bending moment acting at the left side, is positive. Okay. And then we will consider the anti-clockwise moment acting in the right side is positive. Clockwise moment acting in the left side is positive, and anti-clockwise moment acting in the right side is positive. Okay, remember that. So, now if I take, so now this Q dx, this Q I can write, this Q is basically the stresses acting on a wing-class spring. So, if the stresses acting on a wing-class spring, that is equal to K into W. So, this Q will be K into W into dx. Okay. And now, if you see that this Q unit is kilonewton per meter. Okay. So, that means if I multiply, it will be kilonewton, and then this K unit is kilonewton per meter cube. Now, if I multiply with W, it will be kilonewton per meter square. If I multiply with dx, it will be kilonewton per meter. So, that means this unit is not matching. So, actually this K is basically B into K0. So, K is equal to B into K0, where K0 is equal to your modulus of subgrade reaction whose unit is kilonewton per meter square per meter. So, K unit is basically kilonewton per meter square, because K is multiplied with the B. So, remember that this K is K0 into width of the beam, B is the width of the beam. Okay. So, now if I take the vertical component of all the forces 0, then I can write Q minus Q plus dq plus then the upward one, this is K w dx, then minus Q dx, that is equal to 0. So, if I simplify that, I will get minus dq by dx, that is equal to minus kw, then plus q, and then I can write dq by dx, that is equal to kw minus q. Okay. So, now the EI d square w dx square is written as minus m, okay, and q is equal to dm by dx, where m is the bending moment and q is the shear force. Okay. Q is the shear force and this is moment is m, the bending moment is m. So, this shear force is dm by dx. So, I can write that q will be equal to minus EI dm by dx means d3w dx3, and there is a dq by dx term. So, dq dx will be finally minus EI d4w dx4. Okay. So, now you will put this here. So, this will be minus EI d4w dx4, and that will be equal to k into w minus q. So, further if I simplify this equation is EI d4w dx4 plus kw, that is equal to q. So, this is a basic differential equation for a plate resting on spring. Okay. So, this is the basic differential equation for a beam. Now, first I will explain that how you will get the closed form solution, and then I will explain how you can solve these equation numerically also. I will explain how you can solve these equation by using finite difference technique. But here I will give you the idea, because this is the introduction of beams on elastic foundation. I will not go in detail. Suppose if you want to get all this detailed information, then those things are being discussed in another course, that is soil structure interaction. So, you can get you can go to the soil structure interaction part course, and you will get detailed description of beams, plates, and all the nonlinear model, time dependent model, everything. But here it is the introduction. So, I will just give a brief discussion on these beams on elastic foundation. So, this is the basic equation, and then I will try to get the closed form solution, and then I will discuss how you will get the solution by numerical technique. So, once I get this basic differential equation, now if my q is equal to 0, if q is equal to 0, then this equation will be EI d4w dx4, that is will be minus k into w. Now, we can get a closed form solution of this equation, particularly this equation, where load is external load is taken as 0, because that loading effect will be incorporated now by using the boundary condition. But right now q is considered as 0, and I will get a closed form solution, and you know that the getting closed form solution, this type of equation is well known. So, that means we have to take w equal to e to the power mx. So, once if I get w equal to e to the power mx, then I will get the imaginary part and the real part, and finally I will get a solution. I am giving the direct solution of this particular equation. I am not going to detail derivation of this particular solution. This derivation is available any book, or you can also do this derivation, because it is derivation, you know that you have to consider e to the power this w is equal to e to the power mx. So, I am giving the mx, and then you will get the solution of this particular equation. So, the closed form solution of this particular equation is w is equal to e to the power lambda x, and this is C1 cos lambda x plus C2 sin lambda x plus e to the power lambda minus lambda x, then C4 cos lambda x plus C3 cos lambda x, C4 sin lambda x. So, where your lambda is equal to fourth root of k by 4 EI. What is EI? As I mentioned in that previous lecture, the EI is the flexure rigidity of the beam. So, that means here E is the elastic modulus of the beam material, and I is the moment of inertia. So, in this particular case, the I value will be 12 B h cube, which is moment of inertia, where B is the width of foundation, h is the thickness of the foundation. So, this is your I value and E value. So, EI is called the rigidity of the beam or flexural rigidity of the beam, or specifically I should say flexural rigidity of the beam. So, now this is the fourth truth, or you can write this is 4 B K0 4 EI. So, if you have the K0, then you have to put this in multiply by B to get the lambda value, and then C1, C2, C3, C4 are the constant. So, these 4 Ci are the constant. Okay, so, this is the basic solution for this particular equation, where Q is equal to 0, and Ci means C1, C2, C3, C4 are the constant, and this constant we have to determine by your boundary conditions. Okay. So, first I will go, as I discussed about, there are three types of beam: infinite, semi-infinite and the finite beam. So, first I will discuss about the infinite beam, then I will give an idea about the semi-infinite beam, then I will give you an idea about the finite beam, because this semi-infinite and finite beam concept will be used when I will discuss about the lateral loaded piles, because in such case, in such condition, piles will be idealized by semi-infinite or finite length beam, and then we will determine the settlement of the pile due to the lateral load. So, that is why that given that concept is very important in this particular section, so that later on you can use that concept to determine the settlement of the lateral loaded pile. So, first I will go for the infinite beam. Okay. So, suppose this is infinite beam. This is the x direction and both are the x direction. This is infinite, and a concentrated load is acting. And this is the infinite. This is also infinite. Positive, negative is not an important thing, but both are infinite. So, this is P. Okay. Now, if your x is infinite, then W will be tends to 0. If x tends to infinite, then W will be it tends to 0, because at infinite distance there will be no influence of this p, so that your deformation will be 0. And if you look at this equation, this is the closed-form equation that is given, but the previous equation, it is not for infinite or finite, it is for in the general equation. Now, in this equation, if w can be 0 if x tends to infinity is only possible if C1 and C2 is 0. Otherwise, this is not possible, because this is e to the power lambda x positive plus lambda x. So, if you have some finite value of or any value of C1 and C2 or this term, then it would be never 0 if x is infinity. Okay. And this can be only possible if the C3 C4 can present there, because here your e to the power minus lambda x. So, there is a possibility that if your x tends to infinity, then w will be tends to 0, but in the first term it is not possible. So, we have to vanish the first term, and it is only possible if C1 and C2 is 0. So, in this condition is only possible if C1 equal to C2 is equal to 0. Okay. So, that means for this equation is general, as I mentioned. So, you can use it for finite beam also. So, that means for infinite beam, this equation will be reduced to e to the power minus lambda x C3 cos lambda x plus C4 sin lambda x. So, that means this will reduce to 2 constants. Again, these 2 constants we have to determine by using boundary effects. So, what are those boundary effects? Boundary conditions. So, the boundary conditions, the first boundary condition, the due to symmetry, because this it is a you can say the point where the load is acting, you can say this is a 0 point or starting point, and it is symmetric. Now, because infinite, whatever location you place the p beam, p load, it will be the center point of the beam, and that means it is symmetric. So, your symmetric condition slope will be 0. So, I can write slope dw dx, this is slope at x equal to 0, because this is x equal to 0, where the load is acting, will be equal to 0. So, now if I put the slope, if I make dw dx, and then if you differentiate this equation dw dx and put x equal to 0, then I will get C3 is equal to C4. So, once you differentiate this equation, equation 2, this is equation 1. So, if you differentiate equation 2 and put x equal to 0, and that differentiation, I mean that slope is also 0, then you will get C3 is equal to C4, and that I can write C. So, after application of first boundary condition, this equation will be C e to the power lambda x cos lambda x plus sin lambda x. Okay. Now, I will apply the second boundary condition. Okay. The second boundary condition is that, so there will be a reaction, again as I mentioned, there will be a reaction which is given by the spring, and so that reaction is K into W, that K into W is the reaction, and for a small section of dx, total reaction force is into dx. Now, that we have to integrate 0 to infinity. So, if I get the, if I integrate that total reaction from 0 to infinity, then I will get the force that is acting from the top, but that I will get not p, that I will get p by 2, because there is the other half also. I have taken 0 to infinity. That is why I am taking p by 2. So, if you take other half, that other half will contribute p by 2. So, this lower half is taking the p by 2 and this other half is taken p by 2. So, that is why I am taking p by 2. So, that means here if you put this equation w here, so this will be 2 k c 0 to infinity, then e to the power minus lambda x cos lambda x plus sin lambda x, that is equal to 0. So, after integrating this equation and then putting the limits, I will get the constant c is equal to p lambda by 2k. So, after getting these things, I will get p lambda by 2k. So, finally, the equation will be w is equal to p lambda by 2k, that is c e to the power lambda x cos lambda x plus sin lambda x. So, this is the equation of w, and I can write this w as a p lambda by 2k into a lambda x, where a lambda x is equal to e to the power minus lambda x cos lambda x plus sin lambda x. So, this is a lambda x. Similarly, I will get the slope also. That means, I am just giving the how I will get the slope. So, slope is nothing but dw dx. So, I have the w equation, now you do the dw dx, then you will get the slope, and the slope is coming out to be minus p lambda square by k into b lambda x, where b lambda x is equal to e to the power minus, sorry, I have to write in bigger place, or where b lambda x will be e to the power minus lambda x and sin lambda x. So, this is a lambda x, this is b lambda x, equation is given. Similarly, I am giving the expression of moment and the shear force. So, you know the moment is EI d square w dx square, that is equal to minus m. So, m will be equal to minus EI d square w dx square. So, now if I do the d square w dx square, then put those values and simplify it, then I will get the equation of m, that is p by 4 lambda into c lambda x, where c lambda x is equal to e to the power minus lambda x cos lambda x minus sin lambda x. Similarly, I will get the shear force, which is basically dm by dx. So, once you do the dm by dx, then you will get shear force is equal to, the moment is this one, shear force will be p by 2 d lambda x, where d lambda x is equal to e to the power minus lambda x, then cos lambda x. So, these are the equation when the infinite beam is subjected to concentrated load. And remember that all the equations that I have given is applicable if your x is greater than 0. That means, for left side, okay, that is for left side. That means, for in the equation, that means for the left side these equations are given. For right side, if your x is less than 0, then means all these equation will remain same, only the sign will change. How? That means the w x greater than 0 will be equal to W x less than 0. That means for deflection there will be no change, but for slope theta x greater than 0 will be equal to minus theta x less than 0. Similarly, for the moment x greater than 0, there will be no change. That means moment x less than 0. For shear force x greater than 0, again minus shear force x less than 0. That means, if it is the right side or the left side. So, suppose if you want to determine the deflection of a point which is away from the loading point, because due to that loading point, due to that loading, there will be deflection of other points also. So, I can determine the deflection of that particular point. If I want to determine the deflection of the loading point itself, then I have to put x equal to 0. So, if I put x equal to 0, I will get x equal to 0 means sin 0 is 0, there will be cos 1 and this is 1. So, that means, if for at x equal to 0, W is equal to P lambda by 2k. Similar way, I can determine the deflection or bending moment or slope or shear force any point away from the loading point. Now, if the point is towards the loading point, your point of interest towards the left side of the loading point, or your point of interest is towards the left side of the loading point, then this equation you can use directly. But if your point of interest is right side the loading point, or sorry, if your point of interest is this is right side, x equal to 0 is the right side and x equal to 0 is the left side. So, if your point of interest is right side of the loading point, then you can use this equation directly. If your point of interest is left side of the loading point, then your deflection will be same, bending moment will be same, but in case of shear force and the slope, your sign will change. That is it. That means, the whatever values you are getting for the right side, that means x equal to x greater than 0 case, you have to put minus for the left side for the same distance from the loading point. Clear? So, this you have to remember. So, in the next class, I will discuss the other few loading conditions, like I will give the equation for moment, I will give the equation for the UDL, and then I will go for the semi-infinite beam and the finite beam. I will give the idea how you will get the bending moment or the other quantities, that is settlement, by using this infinite beam concept. Thank you.